So in today's video we're going to look at the idea of implicit differentiation. So first let's think about why this is important and what is really meant by implicit differentiation. So say I give you an equation y is equal to x squared. I say find dy dx. Well, we would say the derivative operator with respect to x of y is equal to the derivative operator d dx with respect to x, which is just applying the operator on both sides. And we'd simplify and say that is dy over dx equals to 2x, because we just used the power rule on x squared. That's our derivative. Well, when we have it as y equals some function of x, as we did in this example, that's defined explicitly. But what if we have an equation where we have both y's and x's mixed? For example, a circle, x squared plus y squared equals r squared. And in this case, let's let our radius be 2, so 2 squared is 4. So if we want to find dy dx for this expression, we could try to solve it for y, but to do that we'd subtract x squared, we get y squared equals 4 minus x squared. But then we need to take the square root, so we would get y is equal to plus or minus the square root of 4 minus x squared. And although you can go about it this way, by doing this we have two separate equations that are representing semicircles. The plus is the upper half and the minus is the lower half. So to find the slope on the circle, you would have to determine whether you're working on the upper or lower half of the circle and use the equation, take the derivative that way. Plus the derivative with the square root can be more complicated sometimes than what we would need to do to take the derivative implicitly. So let's look at the idea of taking it implicitly. If we have the same equation, x squared plus y squared equals 4, and we want to take the derivative implicitly, what we can do is apply the derivative operator just like we have in any other instance. So we want d dx of x squared plus y squared equals d dx of 4. Well, we can take the derivative with respect to x of x squared quite easily. We know that's just 2x. But then we have the derivative with respect to x of y squared, which is the implicit part we're going to look at, equal to the derivative of 4, which is a 0, because the derivative of any constant is simply 0. So taking the derivative of x squared and 4 we do just like normal. But since we have this y squared, it's not just going to be dy squared over dx, but we can use the chain rule to take this derivative, because we can say that f of x is equal to x squared and that g of x is equal to y, because that would make f of g of x, our composite function, simply y squared. And really we shouldn't say g of x equals y. Technically you'd want to say g of y equals y, but for the way we're looking at this and applying the chain rule here, I think it's kind of a helpful way to write it out. That's technically not how it should be written. But since we treat y squared as this composite function, its derivative is going to be f prime of g of x times g prime of x. So we know f prime of x will be 2x, because we're just taking the derivative of this. So if we have 2 times g of x, well, g of x is simply y, times g prime of x. Well, what's the derivative with respect to x of y? Well, that's dy dx. So we can say that the derivative of y squared with respect to x will be 2y times dy dx. So in that case, we would say this derivative for the circle is 2x plus 2y dy dx equal to 0. And if you notice, we applied the same derivative rules to taking this derivative. We just multiplied it by dy dx, and that's the way implicit differentiation works. It's really using the chain rule to take the derivative of y with respect to x, where normally we couldn't do that, and it's simply take the derivative of y just like you would as if it's an x, but multiply that derivative by dy dx. So now we want to find dy dx, so we just need to isolate it. So we'll subtract 2x from the equation. We'll get 2y dy dx equals negative 2x. And then divide by 2y, and we've isolated dy dx. So we divide by 2y, and we get dy dx is equal to negative 2x over 2y. And the 2's will cancel, and that's simply negative x over y. So we've shown from that the derivative with respect to x of any circle is just going to be negative x over y. And we can use this concept of implicit differentiation to take the derivative of any function that's not defined explicitly. So anytime we have a function where we have both x's and y's together, we'll just take the derivative as we normally would, only instead of stumbling over a y squared or a y cubed or anything else we may have, it will simply be the derivative as normal multiplied by dy dx. And then we just do the algebra to solve for dy dx in the equation.